Hi, my name is Viet Long Cao, and in today's video I will be doing our assignment 3 for machine learning. And as you can see, this is our professor message for assignment 3, and I will read it out loud. Dear team, I hope you're doing great. The following assignment is divided in two parts. Part A, please run the pre-coded cell to see and understand how convolution 2D kernel works, and at the end respond to the questions number 1 and number 2. Part B, please run the pre-coded cells to train the given neural network, and then respond to the questions from 3 to 10. The idea of the current assignment is to intensify what we have learned about convolutional neural networks, chapter 5 of the Deep Learning with Python book. There are some new concepts and challenges that we will face in the current assignment, and we need to resolve each issue and move to the next step. The assignment is easy to follow, yet needs the patience to solve each question at a time. We'll see about that. Part A, image convolutions. The first step is we have to import the necessary packages and libraries, such as import numpy, from PIL import image, and from SciPy import MISC, from SkyMich, SKImage import data, skimage.color import RGB to gray, import matplotlib.pilot as PLT, import request, and from IO import bytes IO. Second is you import the image. So you get the image from URL like this, and you visualize the content of the response. Oh, and before I continue with the assignment, everything that I'm doing right now is all the code I'm doing in this assignment is already done before recording, because a lot of times when you train the data, it takes forever. It takes way too long to do the process over again. So I'll just do the code, just let it load, and then wait for the result, and then after that, then I'll do the recording. It's okay. So let us continue. 3 is you visualize the content of the response. You print response.content, and then bytes.io buffers the image into RAM. Image.open opens the buffered image. mp.array transforms the image into 3D array containing values from 0 to 255 corresponding to RGB colors channels. And we have this command. First, let's see the image. You plot the resulting image from the array, and then you print the array shape. Compare the values of color channels 0 and 1. Compare the values of color channels 1 and 2. And you have this result right here. Next is you save the color channel 0 into the input underscore image underscore array variable, and you print it. And after that, you visualize the values inside of the resulting array like this. The next section is convolution with 2D kernels. And how convolution works, you can check on this link. So the first task is you create a padded array by adding 2 rows and 2 columns, one of each at the beginning and another of each at the end. Like this, you create a kernel and you create an output array filled with zeros with the same shape of input underscore image underscore array. And then you compare both arrays, and then you apply the kernel to the array values. After that, you plot the resulting array, and you have a nice sport car. Next section is standard convolutions. You define a function to squash out the values between 0 to 255 range. This function will be called in the following function, since the resulting array values can be negative or greater than 255. Define a function to apply a convolutions 2D kernel to an image. Next section is line detection. With image convolutions, you can easily detect lines. Here are 4 convolutions detect horizontal, vertical, and lines at 45 degrees. You create a kernel to detect horizontal lines, apply the kernel to the image, and plot the resulting image. So question 1a and question 1b. Question 1a. Based on the kernels represented on the above image, create a kernel to detect 45-degree lines using convolutions. Apply the car's image and plot the result. This is what mine work. And then and then this is the image. 1B based on the kernels, same as 1A, but this one is 135 degrees. And all I have to do is just on this array, you just do the opposite. Is that we pretty much just do the opposite. Just pretty much you add like a minus sign, so you add like negative to it. You add like negative to positive, it will become a negative, and you add negative to make it positive. So negative 1 here become 1, and negative 1 here become negative 1, and so on and so forth. Edge detection. Question 2. Apply the following kernel to your image and plot the output. And this is it. Right here. Part B, importing libraries. You import the necessary packages and libraries. So you have like import keras, matplot, lib.pilo as BLT, tensor, import tensorflow as TF. And I think I have a problem. No, it's not a real problem, it's more like warning. But before I modified this, it was from keras.utils import to categorical, and there was an error. So I have to put tensorflow dot in order to make it work. Prepare data sets, and then right here you load the data sets. One hardcode target values convert from integers to floats, normalize to range 0 to 1. Building neural network model, you create the model compilations, you display the summary of the model. Custom callback class for logging, create a custom callback class to be called during the training. And instantiate, I think, the custom callback, training the network, and then train the network with train images and train labels, and this is the result. I should have said this before. I should have said before starting the video is that you can pause it anytime you want to see the results more clearly, because I'm trying to scroll it down pretty fast. You plot the results, define a function to plot the results, call the result underscore plotting functions. And now we move on to the question. Question 3 to 10. Did the network present signs of overfitting? If so, in which epoch? And it's yes, the network shows signs of overfitting starting at epoch 10. So I think yes. So it was overfitting with it because it was increasing the accuracy a bit. Like it increased accuracy very suddenly. It's essentially very substantial pace. And I think it starts at epoch 10, which is about right here. It could be around here, but it's easier to say that it starts at epoch 10 right here. Number 4, write down how many layers this model has and identify their types. This model has 5 layers, and you can actually see that in over here. So you have 1, 2, 3, 4, 5. You have 5 layers, and each one has convolution 2D, and then max pulling 2D, and then flatter, and the last 2 is this, which is right here. Number 5. It briefly explains what is the purpose of each of those layers. So convolution 2D is a 2D convolution layer. This layer creates a convolutional kernel that is with layers input, which helps produce a tensor output. Max pulling 2D is max pulling operation with 2D spatial data. It is a sample-based discretization process. The objective is to downsample and input representations, image hidden layer output matrix, etc., reducing its dimensionality and allowing for assumptions to be made about features contained in the subregions bind. Keras flatten class is very important when you have to deal with multi-dimensional inputs such as image datasets. Keras.layers.flatten functions flattens the multi-dimensional input tensors into a single dimensions, so you can model your output layer and build your neural network model. Then pass those data into every single neuron of the model effectively. Dense is the only actual network layer in that model. A dense layer feeds all outputs from the previous layer to all of its neurons. Each neuron providing one output to the next layer is the most basic layer in neural networks. Question number 6. Add one or more convolution layers to your model and run it again. And hint, don't modify the given code, instead copy and paste. So this is what I did. And this is the graph. And I actually made 2, so this is the first one. I made 2, 2, and this is the second one. And again, pause anytime if you feel the need. Question number 7. Compare the results and describe what are the differences between them. And my answer is training accuracy in both pictures, they both goes up, as you can see right here. Specifically, the training accuracy in the first image increases more steadily than the other one, because you can see it's increased more steadily. It's more it's like the way that it increases more stable than this one. Like this one's a bit, I mean, it's somewhat stable, and then it goes up and down for a bit, which is a bit weird. On the other hand, validation accuracy in both figures are quite different. As you can see right here, are very different. For example, the validation accuracy in the first picture changes rapid. I should put rapidly right here, which is my bad. Changes rapidly. For example, the validation accuracy in the first picture changes rapidly as it goes on, but eventually start resulting in an increased graph, which, as you can see here, is a bit hard to see because of the labels, but yes, it's starting from here and it's increasing a bit from here. However, the figure in the second image is more stable and ultimately drops only so ever slightly, as you can see. Question number 8. Add a dropout layer to your model. Run it and compare the result with the previous one. And it's taking a bit long right now. It's taking a bit forever, but I think for now this is the result. Hi, welcome back. I was paused for a little bit for waiting for everything to load once again. So question number 8, add a dropout layer to your model, run it, and compare the result with the previous one. Here you go, and here's my code. Explain with your own words what is the purpose of a dropout layer and how it works. And my answer is dropout is a regularizations method that approximates training a large number of neural networks with different architectures in parallel. A single model can be used to simulate having a large number of different network architectures by randomly dropping out nodes during training. This is called dropout and offers a very computationally cheap and remarkably effective regularization method to reduce overfitting and improve generalization error in a deep neural networks of all kinds. Number 10. Make another modification in the hyperparameters to improve the model's accuracy and compare the final result with the previous one. I made some changes that I've just changed the pouch and the pouch size, and it just turned out to be like this. So it's almost the same as the previous graph. And that's it. Thank you for watching my video, and I see you next time.